Okay, so we will put ourselves into this theory. So we will consider the effect of viscosity to be negligible, and in that case, if we start from an initial configuration, from initial flow where the flow is irrotational, and we have no reason not to assume the flow to be irrotational. If the flow is completely at rest, then it's irrotational. If the flow is just moving uniformly, then it's irrotational. So because the flow is irrotational at the initial time, and because we are not putting any no slip boundary condition, we're going to assume always slip boundary conditions or just no penetration boundary condition, then the flow will remain irrotational, and therefore we can use the Thorson potential flow theory. Okay, so once we say that, the equation that you think about governing the flow is going to be the unsteady Bernoulli equation. It's a simplified version of the Euler equation. It has no effect of viscosity in there, but of course, if you're thinking about waves, what you're trying to model is something which is changing in time. So you don't want to cross out the partial t term. So you have that unsteady term. So we're using. So we're putting ourselves in the realm of potential flow theory. The velocity derives the velocity is the gradient of a potential, because we're also assuming irrotational flow. So remember, irrotational and inviscid, irrotational and incompressible will give you an ideal flow. That means that the potential is actually a solution to the Laplace equation. Note that here in that equation is hidden the mass conservation, the continuity equation. So we assume that the flow derives from a potential, that this potential satisfies the Laplace equation, and we can get to the pressure by use of the steady Bernoulli equation. So once we have this, we have all of the governing equation which governs the bulk of the flow, and all we need to do is apply the correct boundary conditions. Now, what are the boundary conditions where we have a no penetration at the bottom? And so we have to assume we have no penetration. No penetration, or just at the bottom of the ocean, or at the bottom of the pond. So here, essentially, that means that at z equals minus h, we're assuming that the y component, or the z component of the velocity is equal to 0. So we have no velocity in the z direction at the bottom. Right? That makes sense. This is a no penetration boundary condition. And at the deforming interface, we have to impose the kinematic boundary condition. And that kinematic boundary condition we discussed, I think it was week 3, and when we discussed material derivatives. So what is the proper boundary condition for the velocity to impose at a deforming boundary, at the deforming boundary? And that is this boundary condition here, which you may recognize. If you don't remember that, then just go back to a lecture somewhere in September. Okay, so those are the two boundary conditions on velocity that we have to impose, and then we have to impose boundary condition on like stress boundary conditions. And again, because we assume the flow is inviscid, we only can impose the normal stress boundary condition. We cannot impose a tangential stress boundary condition. So the normal stress boundary condition just establishes that the jump in pressure, if there is one, has to be related to the surface tension. If you have a stress boundary condition at an interface, if there is a jump, then that's because of the surface tension. And so you have the jump in pressure, so P atmospheric, P on that side minus P on the lower side is equal to the surface tension times the curvature. Curvature being the second derivative of h if the deformations are relatively small. Okay, so those are all of the governing equations. So all of this I expect you to be able to do and properly explain why we use those equations. Now I'm going to just restate for the last time. Because we assume the flow to be inviscid, once you've done this, then it has implication in the boundary conditions which you impose. So I'm not imposing a no slip at the bottom here. We're not imposing that the velocity in the x direction is equal to 0. If you impose a no slip boundary condition, then you need to have effect of viscosity. Otherwise, actually, mathematically, you cannot solve the problem. Same for the stress boundary condition. If you have an inviscid flow, then you can only impose a normal stress boundary condition. You cannot impose a tangential stress boundary condition. Okay, so you have all of this. So this you have to be able to justify in an exam and to explain why you're getting there. And now the solution method, this usually you will be heavily guided or it will be completely skipped. But the whole point of this solution is that we're just assuming a particular form of a solution, right? And we are looking for a solution where the deformation of the interface will be sinusoidal. Right? So we just plug into, we're just going to assume this here is representing the interface, right? What kind of solution do I need to have a deformation of the interface which looks like a sinusoidal? And because the potential satisfies the Laplace equation, applied mathematicians actually know what kind of solutions will give that kind of deformation. And so we essentially start from this ansatz here for the potential. And so that will always be given in an exam. You will never be expected to come up with your own ansatz for the solution. So essentially you start with that, say, okay, let's look for a solution under that form, and then you just plug it into all your governing equations, right? And once you, and the goal of this is to just look at this here, right? You plug in an ansatz for a solution which depends on z, right? So the velocity will depend on how deep you are in the flow. This is maybe not so surprising. The important part here is this, right? Your solution will have, you're plugging into a solution that looks a bit like a wave, right? If you have an exponential kx minus ct, just think about the real part of that. Just don't worry about the fact that it's an imaginary number. Then you have a cosine kx minus ct, and this represents a wave, which is moving at velocity c. C is the velocity at which the wave moves. Now, we haven't said anything about k, which is the wave number, and we haven't said anything about c, which is the wave speed. And so usually what you do, like the goal here is to plug that solution form into your equations and see how the wave speed relates to the wave number. Right? The wave number, think of it as the inverse of the wavelength. So a high wave number means you have lots of waves, means that the wavelength, think about high frequency in space, so you have a short wave length. A small wave number, right, think about small waves, then you have a high wavelength, a long wavelength. Right? And so the point is just to see, well, if I have waves, like a high wave number, so I have very short wavelength, how fast is this going, how fast is this wave going to move? So you don't assume C and K to be independent. And actually the whole point of this is to find out whether the two will depend on one another. Right? If they don't, then everything just moves as one wave. But when the velocity depends on the wavelength, then the different wavelengths, the different wavelengths will move at different velocity. That's called a dispersion relationship. Okay. Now there's another thing which is important here, is that you're not saying anything either about whether C is real or not. And that comes out usually that will come out into the solution. So if C, if this wave speed which you plug in here is real, right, then you're fine. Then you just have a wave which propagates. But note that if C here has an imaginary component, right, then you will have, and you think about C as having an imaginary part, a real part, plus I imaginary part of C. Now, if it has an imaginary part, then you will have an I squared, so a minus. So you will have certain wavelengths, which will go like for certain wavelengths, you will have here an exponential times a real number times t, which are exponential blow up. That means that this wavelength is going to be very unstable. This is what we're going to see today. Right now, in that case, for gravity waves, if you just looked at the problem, there is no reason why that should happen, because there is no physical mechanism to destabilize the system. You just have a stable stratification with little disturbances. You don't expect much to happen. You're not putting any physics to destabilize the whole system. So, okay, so now once you plug in this solution in there, so you plug into your boundary condition and you plug into your the governing equations, you get two algebraic equations that couples your different parameters, and from there you can extract the relationship between K and C. And that's the relationship we got to towards the end. So just go back to the lectures if you want to see the derivation. Essentially, we got a dispersion relationship which looks like this. So c squared, the square root of the velocity, is equal to g divided by k plus gamma k divided by rho times tangent, hyperbolic tangent of kh. Now, the first thing to note is that this number here is always positive. Right? It's always positive, which means that c is always going to be a real number. If that number was negative, or if that number could become negative, then you have the square of something negative, you know that c would be imaginary. Right? So here it's always positive, which means that you don't have any wavelength that blow up. You have no instability. What you do have is that whenever you have certain disturbances, they will propagate like a wave. Okay? Now there are two physical phenomena here. You have gravity and you have surface tension, right? And both will tend to flatten the interface. Now the two are going to be you see here that you have the wave number, which is 1 over the wavelength. So the relative magnitude of the two, whether gravity is more important or surface tension is more important, and that will have to do with the wavelength or the characteristic length scale of your system, right? And this here, essentially the length here which comes out is the capillary length. So if you consider a wavelength which is shorter than the capillary length, then the surface tension term will become important, which makes sense. And if you're looking at wavelengths which are longer than the capillary length, remember the capillary length is on order of a few millimeters, then the gravity term is going to be the dominant one. So I'm just to show you a bit how does relationship work. Let's assume that we're looking at longer wavelengths, so those for which effects of surface tension can be neglected. In that case, we can neglect that term here. Okay, and so in our dispersion relationship, what we have is the following. We discussed that before. So we get the following relationship. So c squared equals to a change now k for wavelength. Remember that the wavelength is 2 pi divided by, the wave number is 2 pi divided by the wavelength. And then we have two cases. I just wanted to briefly show that. So the first case, we have two cases depending on the number here in the hyperbolic tangent. So when h divided by lambda is a large number, remember that h is the depth of your ocean or of your puddle or of whatever is in your sink. So when the wavelength, right, is very small compared to the depth of the ocean, this is called deep water. It makes sense. You have a very deep layer of water compared to the wavelengths that you are looking at. In that case, this number is going to be large. Actually, this number doesn't have to be really, really large. As soon as it's on the order of 1 or larger, the hyperbolic tangent will be almost equal to 1. It will be almost a constant. If you remember the graph of the hyperbolic tangent, it's almost equal to 1 quite rapidly. If this number here is bigger than 1 or 2 or 3, then it's close to 1. So this term here no longer varies, and what you have is that c squared depends on lambda, or another way of saying that is that your wave speed depends on the square root of your wave length. And this is a typical dispersion relationship. Like your wave, the velocity at which your wave travels depends on the wavelength. So what you will, if you had any kind of feature, you would see the different frequencies, the different wavelengths, which is separate, and you will start seeing actually the larger wavelength traveling faster than the smaller wavelength. And you have it here. C is not proportional, but C increases with the wavelengths. So larger wavelength, larger velocity. So if you're throwing a rock into a pond, you have an initial disturbance. Right. That disturbance is going to split into its different harmonic components. So you're going to see different wavelengths, and the larger wavelengths are going to travel faster. So you're going to see larger disturbances, larger wavelengths moving first out, and the smaller ones are going to move slower. So you're still going to see them propagate behind. Okay, those are gravity waves. Now the other extreme is when h divided by lambda is much smaller than 1. That means that h, the depth, is smaller than the characteristic wavelength that you are looking at. Right? And that happens when you have a very thin layer, that's called shallow water, or that can also happen if you have a feature with a very big wavelength. So think about, a dramatic event on the ocean. We discussed earthquake. That can create a disturbance which will contain larger wavelength, and particularly wavelength which will be larger than the depth of the ocean. In that case, you have something very different that happens, because the hyperbolic tangent will scale. Hyperbolic tangent of x is almost equal to x when x is small. So then this here, the hyperbolic tangent will be roughly equal to 2 pi h divided by lambda, and you see that in that case then those 2 lambda cancel, and when those 2 lambda cancel, then c is equal to a constant. Right? In that case, you don't have a dispersive relation. You don't have dispersion. That means that all of the different wavelengths travel at the same velocity, and your wave speed is the same. So this is why tsunami are so dramatic, because the whole feature just propagates. All the wavelengths propagate. This is also why you see the big waves that you see coming in. They only happen in shallow water. Also, when you want to surf or stuff like that. The big waves, they only happen when the water is shallow. You see a whole feature just moving. It doesn't split into different wavelengths. That only happens in shallow water. Okay, so this is gravity wave. Oh, this is why I wanted to do that, right? Because just to illustrate. Why? There's something I'm not getting there. Okay. So let me just open this. Hold on, I'm missing a file here. I think I saved it in the wrong folder. Okay, no, I'll show you this after the break, because I can't find it. It's in the wrong folder, I think. Okay, well, I'll show you that after the break. Good. So what we're going to discuss now is instabilities. And here I'm not, the algebra is very similar, but much messier than for gravity waves. So I'm going to skip over the whole of the algebra. We'll just rediscuss again, go over with the governing equations. But then it comes down to solving algebraically the relationships to get the duration between your wave number and your wave speed. Then I'll just skip that and give you the answer. Okay, so instabilities are in Kundu. Chapter 11, and I'm going to discuss 11.1 today. Okay, so and we'll discuss instabilities which arise when you have two superposed flows. So superposition of two fluids, I should say. Superposition of So here is our physical system. And actually, we will do two things. We'll discuss Rayleigh-Taylor instabilities, which they will just come as a byproduct, and Kelvin-Helmholtz instabilities. So the two instabilities we'll discuss are Rayleigh-Taylor and Kelvin-Helmholtz. So let's consider an interface. This is our interface. I'm going to put the surface tension. Let's assume there is surface tension. If it was at a very large scale, if you looked only, say, at length scale much larger than the capillary length, then it would make sense to neglect the surface tension because it's obvious. So the top flow we'll call fluid 1, and now we're going to explicitly assume that they have two different densities. Right? I'm not going to say which one is heavier at this point. In one case, the top fluid will be heavier, and in the other case, the bottom fluid will be the heavier. So for now, we are going to assume that this is just what it is, and we're going to assume on top that there is a shear. That means that we have a velocity that the top fluid moves at a velocity u1, uniform flow, and that the bottom fluid here moves at a velocity u2. Okay? And it's a uniform velocity. The arrows look a bit different, but it's a uniform velocity. So the fluid flow, the flow velocity field in the top fluid I will call u1, and we'll have an x and a z component, or an x and a y component, and same for the lower region. We'll have a velocity we'll call u2, and an associated pressure field. Now, the deformation of the interface we'll call as usual h. So if we assume the interface here to deform a bit, and we're going to call h as a function of x and t, the deformation of the interface. So this is our problem. Now, I'm just going to briefly, so we'll derive the governing equations and the dispersion relationship for that system. What we'll look at is then assuming that there is low flow, but that we don't have a stable stratification. Right? So we'll assume u1 and u2 to be equal to 0, but we'll assume rho 1 to be larger than rho 2. In that case, you do have something which might cause an instability, that is the fact that you have heavier fluid on top and lower fluid on the bottom. So there you would expect something to grow. Okay, that will be the first case. Will be the Rayleigh-Taylor instability. And then the second case will be the case where, just like gravity wave, we have the heavier fluid on the bottom, so the stratification is stable. We don't expect anything unstable if the heavier fluid is on the bottom, so if rho 2 is larger than rho 1. But we do have a shear flow. And the shear flow is what could destabilize the interface. Okay, and that will be the Kelvin-Helmholtz instability. Now note that in both cases, you always expect the surface tension to stabilize the interface. Right? Remember that the surface tension is trying to minimize the surface area, and a deformed surface has a larger area than a flat surface. Right? Remember also, just in terms of forces, the surface tension is sort of a force within the interface which just pulls on it to make it flat. So it always pulls in a direction that makes it flat. Anything you do to change to make an interface not flat, surface tension is going to try to make it flatter. Okay. So surface tension, if we do our analysis correctly, it should always look like surface tension has a stabilizing effect. Right? And a stabilizing effect that would mean you need, for instance, to blow harder to destabilize the interface in the case of a Kelvin-Helmholtz instability, or for really Taylor instability, that would mean that for certain wave length, actually, you don't destabilize, whereas all wavelengths are unstable if there is no surface tension. Okay, but just keep in mind that physically you expect the surface tension to always stabilize your interface and to make the system more stable. All right. So just any question on that, by the way, before I move to the gravity equations? Is it clear which system we're looking at? Yeah? Okay. So here are our governing equations. And they're exactly the same as for gravity waves. And so it's just a way of just, again, doing a little review, summary of everything we've seen to that point. So number one, we'll assume an ideal flow for the same reasons as for gravity waves. Right, for gravity waves, it was justified because we assumed that we had a small disturbance of flow from the flow at rest. Let's assume we have complete rest, and we have a no slip boundary condition everywhere, where the flow was initially irrotational, is going to remain irrotational. Right? Here, it's the same, except we don't assume that initially we have flow at rest. Right? If we have a uniform flow, and we don't have flow at rest, but a uniform flow is an irrotational flow. So we have you have a uniform flow. The flow is irrotational initially, and therefore, before nonlinearity and everything might kick in, we can safely assume the flow will remain irrotational, and therefore, inviscid. So we will assume ideal flow. That means that both U1 and U2 will derive from potential. So U1 can be written in terms of a velocity potential, U2 can be written in terms of a velocity potential. And then we'll assume also, of course, incompressibility, and therefore we know that the Laplacian of U1 is equal to 0, and the Laplacian of U2 is equal to 0. So this is here irrotational. We're doing incompressible. That leads to a potential which is a harmonic, meaning it's a solution to the Laplace equation. Okay, this is the ideal flow. Then, so essentially this is mass conservation. Now, how will we get to pressure? We will need to get to pressure once we impose the stress boundary condition, the stress jump at the boundary. So we need the pressure, and the pressure we will get from the unsteady Bernoulli equation. So we have the unsteady Bernoulli equation. And we have that both in fluid 1 and in fluid 2. So we have that partial rho, partial phi1, partial t, plus rho, 1/2, of rho times the norm of u1 squared plus p1 plus rho gz is equal to a constant. Now, the unsteady Bernoulli equation, remember, is valid everywhere in the bulk. It's valid also at the boundary. It's valid anywhere in the flow. And this is the equivalent of Navier-Stokes equation. You write them, remember how we derived them. We took a control volume in the bulk of the flow. So this is valid. When this is valid here. This is valid here, here, anywhere. This is valid at every single point. And in particular, this is valid at the boundary. So we have this for fluid 1, and we have the same for fluid 2. I'm not going to write it. We have the same for fluid 2. Okay, so those are our governing equation in the bulk, and then we have to impose our boundary conditions. So let's start with the kinematic boundary conditions. Now note that here I'm assuming h, so for gravity waves I had an h, a certain depth. You could have it here as well, right? But it's going to make the analysis a bit more complicated, so I'm just going to assume that h is really large. Right? So here I'm not imposing a no penetration boundary condition at the bottom of the ocean or on the Earth. I'm just not going to do that. But if you wanted to look at, for instance, no, I'm too tired. So there's a certain I can't believe I have Faraday waves. If you wanted to look at Faraday waves, then you would have to impose that boundary on the thickness, because the thickness of the bath would be important, right? But here I'm not going to put it. It's not because you never put it. You could of course impose. You could have a certain system with a given depth, and that depth would actually impact the stability. But in that case, it just makes the analytics too complex, and it's not really a phenomenon that we want to discuss. But of course, you could have to impose here on the bottom a no penetration boundary condition at the bottom. Actually, you have to do that if you want to investigate Faraday waves, for instance. So here I'm just going to limit myself to the boundary conditions at the interface. So here this is at interface between fluid 1 and 2. And so what conditions do we have? We have the same kinematic boundary condition that we have for gravity waves. So that is partial h over partial t plus u1 partial h over partial x is equal to v1. Now this is a boundary condition, of course, and you can only impose that at the boundary. It's not an equation which you write in the ball. This is a boundary condition. You only write it at the boundary. And the boundary is actually at y is equal to 0. Now the real boundary, I discussed that on Friday, but the real boundary is at y equals to h. This is where the boundary is. But in fact, because we assume the deformation to be small, we're doing linear stability theory, so we assume everything to be small in a regime where everything is still linear, then it doesn't make any difference whether we impose the boundary condition at 0 or at h, because h is small. Okay? So we impose the kinematic boundary condition for fluid 1, and of course we have to impose the kinematic boundary condition for fluid 2. For gravity waves, we only solved for the motion of the fluid in the lower layer. Now we're solving for the motion of the fluid in both layers. So we have to also impose the kinematic boundary condition for the fluid on the bottom and for the fluid on the top. Now, which boundary condition am I still missing? The stress boundary condition. The tangential or the normal stress boundary condition? The normal. Huh? So that's just related to the jump pressure, to the pressure and jump. So we also have the normal stress boundary condition. And the normal stress boundary condition is the exact same as before. So P, which fluid is on top? Is it 1 or 2? I put 1 on top. So P1 at the boundary minus P2 at the boundary is going to be equal to gamma times the curvature. So H XX. This here means the second derivative of H with respect to X. It's the curvature. So we have the normal stress boundary condition. So you see, the governing equations are the exact same. And so the solution method is going to be very similar. Now the one thing which we have to do, the one thing which is going to be a bit different is in the solution method. Remember that the solution method for gravity waves, we assume an equilibrium state, which was just no flow and a small perturbation. In that case, the small perturbation of the flow is not going to be from the flow at rest, but it's going to be from this uniform shear flow. Yeah? Do you see that? And in fact, you could, if we assume that we have envisaged flow theory, with all of the boundary conditions that we have, there is a trivial solution, right? And that is just one where there is no deformation of the interface. Right? If you have a uniform flow at velocity u2 on the bottom, that satisfies all of your equation. If you have a uniform flow at velocity u1 on the top, it satisfies all your boundary conditions. You have no deformation of the interface, so the pressure on top and on bottom are equal, and everything is fine. You just have a discontinuity in velocity at, at the interface, but you satisfy all of the boundary conditions. Yeah, you see that? So that's the equilibrium. That's sort of a stable solution. An equilibrium stable solution, and what we're going to do is destabilize it a little bit and see how those small disturbances grow or not grow. So in the solution methods, we have to start from an equilibrium state. That's going to be the last point. What is the equilibrium state? So let's look at an equilibrium solution. So we have an equilibrium solution when the interface is not deformed, and that means that h as a function of x and t is equal to 0. Right? So when So when h is equal to 0, how can we write? So if we could write it this way, right? U V1 is equal to U1 0, and U2 V2 is equal to U2 0. Right? That could be a way to write our equilibrium solution, but remember that we don't want to solve for the velocity field, because we're assuming ideal flows. We want to solve for the potential. Okay, so the state, what we are going to assume is a form for the velocity potential. So in that case, what is my equilibrium state for the potential? What is the potential associated with a uniform flow in the x direction? U1x. Huh? So this is going to be U1 times x. And for phi2, it's going to be U2x. Yeah? So this is our equilibrium state. This is a solution to the problem we pose. Right? It satisfies all of our boundary conditions, it satisfies all of our governing equations. So this is where we're starting from, and so therefore what we'll do is we'll look for a solution under the form U1x plus a small perturbation. This here is a small perturbation, and for phi2 it will be equal to U2x plus a small perturbation. Okay? And the whole game is actually to come up with an ansatz for that small perturbation, and actually the ansatz is going to be the exact same as the one we had before, as the one we had for gravity waves. So in the solution, I'm just going to sketch that. So number 4 now. Solution. So in the derivation, we have to come up with an ansatz for the perturbation. And we're going to assume the same ansatz as the one we had for gravity waves. So the ansatz is going to look like a function of z times cosine or exponential I times the wave number x minus ct, and for phi 2 is going to be a to z exponential I k x minus ct. Now, why do we pick this as an ansatz? Again, this is because applied mathematicians worked hard on this, and we actually know that this is going to work. That's essentially how it is. But note that what we're doing conceptually is we are writing a solution phi 1 as the sum of something which we know is stable, or which we don't know is stable, which we know is a solution, plus a small perturbation. And this small perturbation we write as it has the same form as before. So if this small perturbation that we're writing, when we finally reach the dispersion relationship, which will link the wave number to the wave speed, if we find wave speeds that have an imaginary part, then that means that this is going to be unstable. So we're writing this at a little perturbation, and we're going to expect that this perturbation in some cases might be stable. That means that it will disappear. If you perturb the system, the amplitude of that perturbation will decay. It will give you an exponential minus alpha t. In some cases, you might expect that the perturbation will grow. Right? So here you will have an exponential alpha t, where the alpha will be positive. In that case, that particular perturbation is going to blow up. Yeah? So this is what essentially you expect when you plug all of that in the Perron equations. Okay, we'll finish that in the next hour.
Hi, happy New Year. I have a few questions here. But since we have two different fluids, aren't the wave numbers are equal, or depends on the fluid, so we should have K1 and K2, or they are the same, it doesn't matter?
The thing is, if you just have to think about the disturbance. Hold on, let me just stop.